Okay, let's get started. In this lecture, we will go over chapter 2 of our textbook. The goal is to introduce basic concepts like vector spaces, linear vector spaces. They are all the same, as we will see, matrix norms and convergence, and we will examine some specific versions of some specific linear spaces, why they are important, to see their importance. It does no harm if we go back to the Stokey Lucas textbook, especially chapter 3 of the book. In that chapter, Stokey and Lucas describes the basics of dynamic programming, the methods by which we can solve dynamic programming problems. When we solve a dynamic programming problem, we apply the method called value function iteration. So we want to find the value function that describes the value of the optimum actions at any state. And when iterating on a specific vector space in which these functions live, simultaneously we receive the policy function of the problem. So we work in vector spaces. So this is the reason why in dynamic programming, vector spaces or linear spaces are so important. When iterating on a relevant vector space, we converge towards the solution. So we need to interpret, we need to understand convergence, and we also need to understand how we measure convergence. Broadly speaking, convergence is measured by distance. So when we converge to a limit, through this process, we reduce the distance from the solution. So when we converge towards a limit, the distance between a function, a point in general, in a vector space, we reduce the distance between a point in the vector space and the limit, which lies in the same vector space. So this is the reason why we start with the concept of vector space. A vector space is a set of vectors or elements on which we can execute two operations. The first is addition. So when we have two elements, when we have 2 points in a vector space, so x and y are elements of vector space X, then their sum is also an element in the same vector space. So with respect to addition, the vector space must be closed. The second operation is scalar multiplication. If we have a real scalar and we multiply with this scalar an element in a vector space, the result must also be in the same vector space. No surprise, these operations follow the usual axioms. So addition is commutative and associative, scalar multiplication is distributive, and the like. You can check it in the textbook. And in addition, there is a zero element in any vector space. And if we add this zero element to any vector, any point in a vector space, we receive the same element. And if we multiply any point in a vector space, we receive the zero element. Here we have some basic examples for vector spaces. Actually, it's no big deal to check if we have a vector space. We only need to check, we only need to see that these two operations work in a space. The real line or the one-dimension Euclidean space is a vector space because if we add up two real numbers, we receive a real number. So with respect to addition, the real line as a vector space is closed. And if we multiply any real number with a scalar, which is also a real number, we receive a real number. So the real line is closed with respect to scalar multiplication. This is easy to generalize to the n-dimension Euclidean space. If we add up two vectors of n dimension, we receive a vector of n dimension. So with respect to addition, the n-dimension Euclidean space is closed. And if we multiply any n-dimension vector with a real number, we receive an n-dimension vector. So with respect to scalar multiplication, the real line is closed. It can be generalized as a next step to infinite sequences, which can be treated as vectors. It's not, so I wouldn't say it elegant, but it works. So the space of infinite sequences is like the space of vectors or finite sequences. So everything works exactly like in the finite case. Very important, a final note. The presence of a zero element in a linear space is a prerequisite. When it comes to talking about subspaces of linear spaces, we will see that the presence or the absence of a zero element in a subspace, in a set, is key, because a subspace of a linear space must also be a linear space, so it must contain the zero element. So if there is no zero element in a set, in a subset of a linear space, then this subset cannot be a subspace. So the zero element, once again, the zero element is a prerequisite for a set to be a subspace. Let's go on with subspaces and linear combinations. What is subspace? It is a non-empty set if we have two elements in this subset and the linear combination is in the same subset, then this is a subspace. It is, okay, just to be on the safe side, as it is a subset of a linear space, then these two elements are in the vector space, in the linear space, and the linear combination is also in the same vector space, because M is a subset and a subspace at the same time of a vector space. So given that the linear combination is in the subspace, this linear combination must be in the linear space too. A subspace is non-empty, so it must contain at least one element, and it must contain the zero element too, as I have just mentioned at the previous slide. So it is a linear space, so it must contain the zero element. A trivial example: in the three-dimension Euclidean space, a subspace is a line that passes through the origin. So a subspace is a generalization of a plane or line through the origin. Some consequences: the intersection of subspaces of a vector space is a subspace of the vector space, but it doesn't apply to the union of subspaces. So we cannot say that the union of subspaces is itself a subspace. So instead of using unions, we define the sum of subspaces, which is different from the union of subspaces. What is the sum of two subspaces or subsets? If we have two subspaces S and T, their sum is a set that contains the sums of vectors coming from the two subspaces respectively. And it is true that if S and T are subspaces of a linear space, then their sum is also their sum is a subspace. So the sum of two subspaces is a subspace. Linear combination, I know you are familiar with linear combinations, so we can go over it very quickly. If we have a set of points or vectors from a linear space, a linear combination of vectors are interpreted in the usual way in our textbook, and it is trivial, but I mentioned that if we have a linear space with vectors, their linear combination must be in the same vector space, because linear spaces are closed with respect to scalar multiplication. So if we multiply any vector with a scalar, it is in the same vector space. And if we add up elements from a vector space, we remain in the same vector space. So linear combinations are always in the same vector space. The subspace, let's jump to the subspace generated by S, where S is a subset of a linear vector space, and the subspace generated by S contains all vectors in the vector space that are the linear combinations of the vectors in S. So points in the subspace generated by S are linear combinations of points in S. So S is a subspace. S is a subset of a linear space. So we have vectors in S, which is a subset. And if we create the linear combinations of these vectors in S, we will have a set which is called the subspace generated by S, and it contains all the linear combinations of the vectors in S. Question: how do we know that the linear combinations of points in S are in X, I mean the vector space? It is trivial, because X is a vector space, so it is close to linear combination, as we have pointed out. A trivial consequence: the subspace generated by S contains S, the subset, because any vector in S can be constructed as a linear combination. So any vector in S can be described as a trivial linear combination. So any point in the subset S must be in the subspace generated by S. To dig deeper in subspaces and linear combinations, let's have a look at problem 3 on page 43. So we need to show, this is problem 3, and we need to show that the subspace generated by the union of M and N is equal to the sum of M and N. The proof is built on the two operations that we define in the text. First, so we need two operations. First, the subspace generated by a set. This set is called the subspace generated by S. It consists of all the vectors in X, which are linear combinations of vectors in S. In other words, the subspace generated by S contains all the linear combinations of S, and these linear combinations are in X, the linear space. The other, this is on page 16 of the book, and the other is the sum of two sets. This is on page 15 of the textbook. The sum of two subsets M and N in a vector space consists of all vectors of the form all vectors in this form where M comes from the subset M and vector N comes from the subset N. The proof consists of two steps. In the first step, we show that the sum is a subset of the subspace generated by M union N, and the second step is the reverse. The subspace generated by M union N is a subset of M, the sum of M and N. So let's proceed step by step. In the first step, our strategy is simple. We have a vector from the sum of the sum of the two sets, and we show that it implies that the same vector is also in the subspace generated by M union N. Okay. So we have this vector, which means that X is the sum of two vectors such that M comes from M and N comes from N. It is obvious that M is in the union. From this it follows. And N also is an element in M union N. So if we say that X is the sum of two vectors, then X is a linear combination. Then X is a linear combination of M, of vector M and vector N, and as M is in the union of M and N, and also is also in the union of M and N, it follows that X is in the subspace generated by M union N, since X is a vector which is one of the linear combinations of vectors in M union N. So it follows that X is in M plus N, which is a subset of the subspace generated by M union N. So once again, as M is an element of the union of M and N is also a vector in the union of M and N, X is in the subspace generated by M union N, because X is a vector which is a linear combination of vectors in M union N. So this is the first step. So actually, the result is the sum of M and N is a subset of the subspace generated by M union N. And this is what we wanted to demonstrate in the first step. In the second step, we have a different strategy. We will do the exact opposite. The exact opposite of the previous step. We have a vector X as an element of the subspace generated by M union N, and we will see that from this it follows that X is in the sum of M and N. So we have this vector as a vector from the subspace generated by M union N, and please remember the definition. This subspace contains all the linear combinations of vectors in M union N. So in this case, vector X, can be described as the linear combination of vectors from M union N. Formally, X is a linear combination of vectors from M union N. Formally, X can be described as a linear combination where the scalars, di scalars, they are real scalars. So we have real scalars. These vectors come from M, or they come from N, or both. We cannot know. So importantly, M and N are subspaces by assumption. It means that a linear combination of vectors from M are in M, and any linear combination of vectors from N remain in N. See page 14 of the book, and we will use this characteristic in this proof. So once again, the linear combination of vectors from M is in M, and the linear combination of vectors from N is in N. There is a problem, however, in the case of vectors which are in both M and N. But we can solve this in a very easy way. If we have such vectors that are in both M and N, let's sort them into M. Okay, if we have vectors from
both M and N, so if they are in both sets, then let's say they are in M. And in this case, we can say the following. M is a vector that can be described as a linear combination of vectors in M. So these vectors, they are in M, but not in N. And in this case, M, the vector M, is a linear combination of vectors in M, only in M. And by contrast, N can be described as another linear combination, as a linear combination of vectors in N, only in N. And as M and N are subspaces, these linear combinations remain in M and N respectively. So this is the key feature of M and N. They are subspaces. So we simply decomposed the linear combination creating X into two parts. One part as a linear combination remains in M, and another part remains in N. So we can say, if consequently if we say that X is the sum of two vectors where M is in the set M or subspace M, N is in the subspace N, then X is in the subspace generated by M union N, which is a subset of M, the sum of M and N. And by the second step, we have demonstrated the equality.
The next set of concepts is the translation of sets and linear varieties. But before moving to the translation of sets, let's go over a further related consequence. The subspace generated by S is the smallest set containing S. If M is a subspace that contains S, then M also contains the subspace generated by S, because if S is a subset of M and M is a subspace, then it is close to linear combinations, so it contains all the linear combinations of the points in S, which is the subspace generated by S. So the subspace generated by S is a subset of M, and the reverse doesn't apply, and the subspace generated by S cannot but be the smallest subset containing S. What is the translation of sets in a vector space? Intuitively, we can say that when we translate a set in a vector space, we shift it, the whole set. We shift the whole set in a given direction. So actually, we add the same vector to all elements in the set. So we can translate a set in a vector space by adding the same vector to all the points, to all the elements in the set. And if we can translate any set in a vector space, we can also translate a subspace in a vector space. So we can translate a subspace M in a vector space by shifting it with a given vector. the result is a linear variety, V, which you can see is the sum of a subspace and the given vector. Figure 2.2 is very instructive because in this figure we can see that M, which is a subspace, can be translated into V by any vector in V. So even if M is unique and V, the linear variety, is unique, the vector by which we translate M into V is not unique. So any vector in V does the job of the translation. This is an introductory course, so no surprise. We go on with basic concepts like convexity, convex cones, and linear dependence and independence. Convexity, to begin with, convexity is a key concept we use in many theorems and applications. For instance, in dynamic programming, we need to check time and again, in every application actually, if some sets we work with are convex or not. Convexity is based on the concept of convex combination. If we have a set in a linear space, we pick 2 points, 2 vectors, 2 arbitrary points in this set, and if we describe the line between 2 points, actually any 2 points, then we need to check if the lines between 2 points, between the arbitrary 2 points, if the lines are in the same set, then the set is convex. So this is the reason why I'm saying that convexity is based on convex combination. We need to describe the lines between 2 points, and the lines for any 2 points must lie in the same set as the 2 points, and then if this is so, the set is convex. We have some basic results. If we have a convex set K, then alpha K for any real scalar is also convex. The sum of 2 convex sets is also convex, and the intersection of convex sets is also convex. The related definition is the convex cover or convex hull of any arbitrary set. This arbitrary set is not supposed to be convex. The convex cover of this arbitrary set is the smallest convex set that contains S. We will dig deeper in the concept of convex covers with problem 4 on page 43, which will be do in turn. And linear dependence and independence, they are household concepts, so we can go over them very quickly. They are worth reviewing. A vector x is linearly dependent on a set of vectors if this vector, this point, can be expressed as a linear combinations of the vectors. So in this case, if this linear combination is existent, then we say x is linearly dependent on this set of vectors. Otherwise, x is linearly independent from the vectors. We can check, this is elementary linear algebra, we can check the linear dependence or independence of vectors. A necessary and sufficient condition for linear independence is for a set of vectors, from a set of vectors, if the 0 vectors can be described with 0 weights, then this set of vectors is linearly independent. A related result, if a vector can be expressed as a linear combination of vectors, then this expression is unique. So if we can describe vector as a linear combination of vector, then this representation is unit. We cannot find another representation for the same vector. A related concept is the basis of vector or vectors, or a basis formed by vectors. There is a set of linearly independent vectors. They form a basis for the space X if all points in X can be expressed as linear combinations of these points, of these vectors in this set S.
So this is problem 4 of the book, in chapter 2 of the book. So let's have a set of vectors x1, x2, xn, and a convex combination of these vectors is a sum of scalar multiplications. This is a linear combination where the weights are non-negative, but their sum is 1. This is a convex. This is a convex combination. So let's have. So this is the concept. This is linear. This is convex combination. This is a form of linear combinations. This is a linear combination where the sum of weights is 1 and the weights are non-negative. So, okay, this is the basic. Let's have a subset of a vector space. This set is called S. This is arbitrary. This is an arbitrary subset of a vector space. Okay. K is another set. It contains all the linear combinations, all the linear, not linear, convex, sorry, my fault. So K contains all the convex combinations of vectors in S. So it contains all the convex combinations of vectors from S. And we need to show that K is the smallest convex set containing S. This is the smallest convex set containing S. The proof is similar to problem 3. We need to show, we have 2 steps. We need to show first that K is a subset of the smallest convex set, and second, the smallest convex set is a subset of K. Okay, so let's go step by step. In the first case, if these vectors are from S, then any xi is an element of the smallest convex set that contains S. Formally, xi is in the smallest convex set that contains S. Okay, we know that this set is convex by definition. This is convex by definition. For this reason, the convex combination, a convex combination of any vectors xi from S, it is also in the smallest convex set containing S formally. So given that this set is convex, it follows that any convex combination of vectors from S which we call y1, it is in this set, where x1 and x2 are in S, which is a subset of COS, and for the convexity of COS, it is true, it holds, it applies, it holds. It holds that y1 is also in COS. Okay, so let's take the next step. As y1 is in COS and x3 is an element of S, so it is an element of COS, any convex combination this is a convex combination. Please check the sum of the weights. It's straightforward to see. This is y2, and it is, of course, in COS. So y2 is another convex combination. But we must realize that we can expand this part of this expression. So we can say that y1 can be described as another convex combination. This convex combination comes from the previous step, alpha 3, 1, 2, 3, x1, x2, x3. So from this, it follows that y2 is a convex combination of x1 x2 and x3. Generalizing this pattern, we can say that this vector oh geez. n. Please note, this is 1, this is 1, this is 1. So finally, we can say that it is a convex combination. So it must be in COS. So all these yn vectors can be described as the linear combination of linear combinations of vectors in S, also in COS. So consequently, all these vectors are in COS. And at the same time, they are in K. As K consists of vectors which are convex combinations of vectors in S, it follows that K is a subset of COS. Okay, so the logic of problems 3 and 4, the logic is the same if we have a certain type of vector making up a set, just like in this case with vectors y n minus 1, making up set K, and these vectors are all elements of another set, like in this case y n minus 1 vectors are in COS, then it follows that set K is a subset of COS. In the second step, let's demonstrate the second part of the claim. It is true that to any vector in K, any vectors in K, any vectors to any vectors in K, we can find weights and vectors such that X is a convex combination Y is a convex combination. So the sum of the weights in both cases are 1. Okay, so it is by definition, please note that set K is by definition a set that contains convex combinations. So actually X and Y, they are in K. Let's pick some lambda. What do we know about the convex combination What do we know about this convex combination? Let's expand the expression. So instead of y and x, we will use the convex combinations. It equals to, we can relocate lambda and 1 minus lambda after summation sign plus. So what we are interested in is the weights. So let's focus on the weights by expanding this part of the expression. We can realize this pattern. By factoring out lambda and 1 minus lambda. This is 1. And this is 1. So, actually, this is 1. So this is the sum of the weights is 1. So, consequently, this convex combination, this is a convex combination, is in S. Sorry, this convex combination is a convex combination of vectors in S, so it must be in K. So this convex combination must be in K. And consequently, please remember, y is in K, x is in K, and a convex combination of vectors in K is in K, so K must be convex. Consequently, K is convex because a convex combination of two vectors in K is in K, so K is convex. As vectors, as convex combinations, as convex combinations of vectors from or in S or in K, then S is a subset of K. Hence, by definition, COS is a subset of K. As any vector which is in COS, it is also in K. One final remark: what does it mean by definition? By definition means that as this set is a subset of K and K is convex, and COS is the smallest convex set containing S, then COS is a subset of K. Okay, so yes, the proof is complete.
So far, we have worked with some basic algebraic properties of vector spaces. To go further, to have some topological concepts like openness, closure, convergence, or completeness, we need to measure the distance in the space. In this context, convergence is of key importance. When we talk about convergence, we talk about processes in which we are approaching a point in a linear space, in a vector space, by reducing the distance from this point step by step. So we cannot talk about convergence without talking about distance. So we need to measure, we need to define, understand, and measure distance in a linear vector space. To this end, we need norms and metrics. Our textbook discusses norms only, but Stokey and Lucas discusses both. They discuss both. A metric is a distance function on a metric space that measures the distance between two vectors. Norms measure the length of a point of a vector in a linear space. As Stokey and Lucas argue, norms can be used as metrics. So we can measure the distance between 2 points that takes a metric by measuring the length of the distance vector, which takes a norm. So I have a simple example. We have 2 points in the two-dimension Euclidean space, -3, 3, and 2, 4. They are 2 points. As the two-dimension Euclidean space is a linear space, it is closed to addition. So the distance vector, which is -5 and -1, -5, -1, it is also a point in the same two-dimension Euclidean space. We can use the Euclidean metric to measure the distance of the 2 points in the usual way. It is a real number. You can see 5.09. And with the same, or related, not the same, but the related Euclidean norm, we can measure the length of the distance vector, and we have the same result. So this is the way how Stokey and Lucas show in a very instructive way that we can use norms and metrics to measure distances in a linear space. And if we see this, then the definition of norm linear spaces is easy to state. A norm linear space is a space, it's a linear space in which we can measure the distance between any 2 points. So norm linear spaces. Just for the sake of good order, I like to emphasize that vector spaces are often called linear spaces, and you can read the expression linear vector spaces in the textbook, but don't get intimidated by these expressions. They mean the same. So a norm linear vector space is a vector space with a norm on it, by which we can measure the length of vectors in the vector space. In general, a norm is a function that assigns a real number to any element in the vector space, which we call the norm of the element. A norm satisfies three basic axioms: non-negativity, the triangle, inequality, and scalar multiplication. We have two important consequences. One is related to the difference between the norms of 2 points in a vector space, and the other is quite trivial. So the norm of the distance between x and y is the same as the norm of the distance between y and x. So I think it's obvious, it's trivial, but like many trivial things, its formal proof is a bit tricky. Okay, if you see the way how you can prove it, it's simple, but you need to think about it. So once again, the norm of the distance vector between x and y is the same as the norm of the vector between y and x. So let's see some examples for norm-linear vector spaces, or simply norm-linear spaces. The undimensioned Euclidean space with the Euclidean norm is a normed linear space. The linear space of continuous functions on the real interval AB with the norm interpreted as the maximum of a function on over the interval is a norm. So the norm of any function x from the space of continuous functions over the real interval is simply the maximum of the function over this interval. Bounded variation, so the linear space consisting of functions of bounded variation on the real interval AB with total variation, which is defined as the supremum of the function over the partition. It's a bit tricky. So we can perform a partition of the interval AB. We can find any partition of this interval, and we calculate the variation, the total variation of the function with respect to this partition. So we compute the absolute values of the changes of the function over this partition, and with the supremum we seek the maximum, actually the highest value of the variation of the function over the partition of this real interval. So this is the total variation. Note that the definition claims that functions of bounded variation belong to this vector space. Bounded variation means that this total variation is finite to any partition. Okay, so we have a function, we have arbitrary partitions of the real interval AB, and if this total variation is finite to any partition, then the function has bounded variation. Okay, so these functions constitute the vector space BVAB, and we have the norm. So this norm, which is the sum of the absolute value of the function over A and the total variation of the function, which is the highest value of any partitions over any partitions. For the constant function, the total variation is 0. And if we have a monotone function, then total variation is the absolute value of xa minus xb, or xb minus xa, all the same. So these are some basic examples for nonlinear spaces. Okay, so interior and closure of subsets. The interior of a subset is the set of all interior points of the subset. So to define the interior of a subset, we need the definition of interior points. A point is an interior point if all the points in the open sphere around it with radius epsilon are in the same subset. So what is an open sphere in the first place? An open sphere in the two-dimensional Euclidean space, an open sphere is a circle around the point with radius epsilon. In the three-dimensional Euclidean space, an open sphere is a sphere around the point with radius epsilon. It can be generalized to higher dimensions. Very importantly, epsilon is not arbitrary. So when it comes to checking if a point is an interior point or not, we must be able to find a non-zero strictly positive number epsilon, which serves as the radius of an open sphere around the point. And if points in this open sphere are in the same set, then the point is an interior point. So epsilon is not arbitrary. We must be able to find a positive epsilon to a point. And if we are so, and we can draw an open sphere, a circle, a sphere around the point, then the point is an interior point. The closure of a subset is very similar, and it is related because the closure of a subset is the union of the interior and the boundary. Stokey and Lucas also use the boundary of sets. On page 358, they define the boundary of a set as the set of points serving as the limits of sequences inside and outside P. Intuitively, a point is a boundary point if the open sphere around this point for any epsilon contains at least one point in the interior and another point, at least one point not in the interior of the set. And P is closed if the set is equal to its closure. Some important results. The complement of an open set is closed, and the complement of a closed set is open. The intersection of a finite number of open sets is open, and a union of open sets is open. The union of a finite number of closed sets is closed, an intersection of closed sets is closed. And if P is convex, then its interior and its closure are also convex. Closed sets have an important convergence property. If P is closed, then every sequence in P has its limits in P. So, in other words, every sequence in the subset converges to a point in the same subset, to a point in P. So, finally, we can define the convergence. It is a property of sequences in vector spaces. If a sequence converges to a point, if xn converges to x, we say that the limit is x, by which we mean that the distance approaches 0. So if we have a sequence, and if sequence is set to converge to a limit point, then the distance between subsequent elements of the sequence and the limit point the differences are decreasing. So we get closer and closer to the limit point. Very important. We will discuss convergence in various vector spaces. And in all cases, convergence is measured by the norm of the vector space. So if we discuss convergence in a normed linear space, we always measure convergence by the norm of the normed linear space. On the real line, convergence is obvious. So when we converge, if we have a sequence of real numbers on the real line, we say that we converge to a real number if the distances between subsequent elements of the sequence and its limit is the distances are decreasing. In the n-dimension Euclidean space, very important, in the n-dimension Euclidean space, convergence implies the convergence in every dimension. So if we have, for instance, the 3-dimension Euclidean space, if we pick a point in this space, we converge to this point, to this limit point, if and only if we have a sequence of points and the distance between every dimension, measured in every dimension, is decreasing. These spaces are of special importance. For instance, in general equilibrium theory, we find an optimal allocation. And to show that this is also a competitive equilibrium, like in the case of the one-sector growth model, we need to show that there is a price system, a related price system that can support this optimal allocation as a competitive equilibrium. And price systems live in the dual spaces of the spaces in which we have the solution. We will review, in this course, we will review the concept of dual spaces and all the related concepts. So these spaces, please trust me, these spaces are of special importance. These spaces consist of infinite sequences and continuous real functions, measurable functions, respectively. For instance, when in dynamic programming, we are supposed to find an optimum capital path or investment plan for the firm, in the discrete time case of dynamic programming, we will have the solution as an infinite sequence. This is a normed vector space with the norm. The definition is based on the sum of the powers of the absolute values of the elements of the infinite sequence. P in the norm and in the definition is finite or infinite. If it is infinite, then we have the space of bounded sequences to which the norm is simply the supremum. So we have an infinite sequence, a bounded infinite sequence to which we can find the least upper bound or simply the maximum. We have the Hölder inequality, which is very useful in some optimization problems. This is an inequality, but in a special case, it applies with equality. And finally, let's leave the space of infinite sequences for the space of real measurable functions to which the power of the absolute value of the function is Lebesgue measurable. This is an important prerequisite because as you can see, we calculate the norm of a function with an integral, and we calculate the integral with a measure, a Lebesgue measure. So this is the reason why we need Lebesgue measurability as a prerequisite. In this case, P is finite, but P can be infinite, just like in the case of the space of infinite sequences. In this case, we use the essential supremum, which is similar to the supremum, but it is essential supremum. So we exclude those parts of the interval AB, the measure of which is 0. So simply put, we say that the essential supremum of a function is alpha, which means that the function can be higher than alpha only over such parts of the interval AB where the measure is 0. We have the Hölder inequality for functions, which is very similar to the case of infinite sequences. So basically, we have an inequality, but under a special circumstance, it applies with equality. And as you will see in the next two exercises or problems, the Hölder inequality is very useful when we are supposed to find a function or sequence to maximize or minimize an integral sum. In the first problem, we need to find a continuous function on the interval -1, 1 that maximizes the integral, the following integral, and then we will find another function with the same specific constraint that minimizes the integral. So let's do these two exercises in turn.
So let's solve the first problem. The LP space, what is this space? If P is higher than or equal to 1, then this space consists of continuous and integrable functions to which this power is Lebesgue integrable. So the norm of a function from this space is this integral, which shows why we needed to set as a prerequisite the integrability of the function. The Hölder inequality is claims that this integral cannot be higher than this expression based on the norms of the two functions. So these were the basics. So in the exercise, in the problem, we are looking for a function xt, on this interval to maximize this integral. Subject to the constraint on x Okay, so this is an optimization problem. So to solve this problem, let's use the Hölder inequality. So in this form, we need this form of the Hölder inequality with equality if and only if and only if this equality holds. Okay, almost everywhere on the interval AB. All right. From this criterion, an interesting fact follows. We can describe the function xt on the basis of the other function and the norm of function x. So we need to maximize an integral. So this is the objective function. With the constraint, and to use the Hölder inequality, we must say that x is in space LP and y is in LQ. Okay, and let's say that this is function yt, and from this constraint, where is the constraint? Here is the constraint. From this constraint, it follows that p is 3. So given that 1 over p plus 1 over q is 1, it follows that q is 3 over 2. Okay, so as a first step, we identified the two functions, one in space LP, the other in space LQ, and we have the numbers p and q. So unknown function xt. This is the function we are looking for. Of this function, we know the following. It comes from the constraint. Okay. So we know this for sure. And now we can use the Hölder inequality. And the integral cannot be higher than this expression, of which we know that it cannot be higher than okay. So this is that we know this for sure, and this is what we need to calculate. The good news is that we can calculate the norm of function y with no problem. So the norm of this function is simply this real number. Okay, and this, we can calculate this integral. Why? Let me draw a figure. 1 minus 1, 1 minus 1. So this is the basic function, and this is its absolute value. Okay, and the absolute value is symmetric to the vertical axis. So to calculate the integral, which is this area, we only need to calculate this part of the function, of the integral. So we only need to work only on this interval. Here we don't need to pay attention to the absolute value because the function is positive, non-negative actually. So here we have this function, and the integral is simply between 0 and 1, 2 over 11. And over the whole interval, from this the norm of the function over the whole interval is simply this real number. Okay, so this is the norm of the function. So to go back, yep, let's pick up where we left off. So we can say that it is equal to, I'm just using these results. To add 1 over 3 to square 2 over 3 multiplied 11 add minus 2 over 3. So after a few steps we receive this number as our result. So to sum up, to summarize, this integral on the basis of the Hölder inequality, it cannot be higher than this real number. And please note that this integral is very similar to the objective function. Not the same, but very similar to the objective function. All right. So, under what conditions does the Hölder inequality hold with equality? it holds with equality if and only if the norm of the function is this. Okay, so this choice, choosing function x in this way, we can maximize. This is important, so let me emphasize it. So by choosing function xt xs, the norm is this, then we maximize this integral. The only fly in the ointment that this is, it contains an absolute value. If we know the norm of this unknown function, so please note that we know the norm of an unknown function, so with this in the bag, we can go back to the Hölder inequality, on the basis of which we described the absolute value of the unknown function x, which, okay, I won't describe the whole process, the first step and the final step. Okay, I think it's okay. And after a few steps, we receive this expression. Okay, so this is the absolute value of the unknown function we are looking for. We are very close to the unknown function xt. We know its absolute value. So by choosing, once again, by choosing the function so that its norm is 2 and 1 over 3, then this integral with the absolute value is maximal. Yes, so the absolute value in the integral, so the integral is maximal, but of this, it is true that this integral without the absolute value cannot be higher than the integral with the absolute value. And this inequality holds with equality if and only if the integral the integrand on the left is always positive. So the sign of xt is the same as the sign t3 eventually as the sign of t. So we need to play with the signs. With the help of the signum function. So we need the sign of t, and that is the solution. And in the final problem for the day, we have a new objective function. We need to minimize this integral. Its minimum can even be minus infinity. So the following inequality holds. This minimum, so the minimum of this integral cannot be lower than this integral. Okay, the integral on the right ranges from 0 to minus infinity, from 0 to minus infinity, and the left hand side, the integral on the left hand side cannot be lower than minus infinity, but it can be, the integral on the left can be positive, even positive, we don't know. So this inequality holds for sure. And finally, we can return to the previous problem. Okay. So it holds for sure. So eventually, by highlighting the two ends of this expression, we have the following result. And the right hand side is familiar from the previous exercise. Okay, so the value of the integral on the right is the same as it was previously in the previous exercise, and we take we multiply it, simply multiply it by -1. So just a kind reminder to the previous problem. By choosing x function x such that its norm is this real number, by this choice we maximize the integral containing the absolute value. From this, we had the absolute value of function x, which is still relevant even in this problem. So, given that we know the absolute value of this unknown function xt, we want to minimize this expression. And where is it minimal? It's easy. Where it is minimal, where this function is negative everywhere and is positive nowhere. So, in other words, where xt, the function xt, is negative, where t is positive. So, the solution oh geez, this is an absolute value. And the signum function of t. So where t is positive, its signum is positive, but xt has the opposite sign. And this is the solution to the problem.